شايفين السلايدز؟
Yeah.
كذا شو واضح يا دكتور.
طيب. I have a couple of announcements before I take any of your questions. Today, inshallah, within an hour, right after class, you will see homework number 1 posted on Blackboard. You are requested to answer the homework within a week and upload it to Blackboard. If you find any difficulty in that, just let me know. You will also find, it's on chapter 2, the aerodynamics, a couple of problems. So you will do the homework, the instructions are there, scan your work and upload it to Blackboard. Also, there will be announcements on the regarding the quiz number 1 on Wednesday, inshallah. After submission of the homework and you see the answer and you have any questions. So it's going to be on Wednesday next week, Wednesday of week 4. That's going to be our first quiz. It's only on chapter 2 aerodynamics, and that's it.
Doctor,
yes,
I think the next Wednesday is the National Saudi Day.
صح ما شاء الله عليك. طيب, the other section have not corrected me. طبعا I should have noticed, of course. Okay. يلا كل عام وانتم بخير يا شباب. كل عام وانتم طيبين. And then in that case it will be Monday week 5. Yes, that makes sense. Monday week 5. Okay. So you realize if you already got the textbook that there is a lot of reading in there in the textbook, and that's to get good grasp of the subject. But when it comes to quizzes and measures, I will only test you in the parts that we covered in here. So the parts we have the lectures. That's why in the announcement for the quiz, you will see it's specific to certain pages. So it says from section to section or page to page and so on. These are the parts that will be included in the quizzes and the measures. Okay. Please make use of the office hours from now until the quiz time. Stop by, have questions in Teams or whatever platform you are comfortable with. I will always be on Teams, but we can have an appointment on another platform another time. Feel free to ask on WhatsApp, email, whatever. So don't wait until the last minute because there's going to be some extensive reading before that. Hopefully everyone got the books.
Not yet.
Oh, okay.
Not yet.
Inshallah, before that time, you will be getting the books. If you do the homeworks, read the slides, that should be fine for the quiz. Okay, but reading the specific pages that are assigned in there, look, they have like extra examples that will help you in preparing for the quiz. Okay, now it's time for your questions. If you have any questions for me, whether in the material, on the way, or the way things are going to go, if you have any comments, please feel free to share them. Maybe not here if you're going to take time. If you have comments on the way the online teaching is going on, if you have any suggestions, if you have different platform, whatever would make the experience more beneficial for everyone. I'm going to do some changes in the way we're conducting this, so we're going to be including some of the polling apps. So we're going to see if Kahoot will be fine or if I can use the Teams polling tool. So whatever you're more comfortable with, just let me know so that we can go on with this. As for attendance, I'm counting on the class list that I will get from Teams, but every now and then I will be asking questions and I expect to get an answer, whether the answer is the correct answer or the wrong answer, or I don't know. But if you do not respond to my questions within the lecture, then I might assume that you are not in front of the screen as we go through the lecture. And in that case, attendance grade will be affected. Okay, so it's not just logging on and that's it. So it's important to respond even if you don't know the answer. Okay, any questions? Comments, suggestions? Now it's very difficult to have 36 students in one class without a single question, because it means either everything is fine or there isn't really, we haven't picked up on the reading or material. So I expect questions. Typically the 5 minutes are not enough to answer the questions for all. So let's see how it goes next time. Okay, so thank you for correcting me on the quiz date. I will correct that on Blackboard. So what we're going to do today, we are going to start chapter 3, which is titled Some Propulsion Characteristics, because it doesn't deal specifically on all the details of propulsion. You will get these in other courses of your curriculum. You will get them in Gas Dynamics 325, then in Propulsion AE 422. But for us here, we will pick some propulsion characteristics that are important for us in the conceptual design, in the initial design of the aircraft. So we're going to discuss the different types of engines from a design point of view, the main design parameters that we rely on for these engines, and some rough calculations to estimate these parameters that we're talking about. Okay. So we will start by defining the two parameters that are important for a design engineer when he uses an engine, the thrust and the efficiency. What's the difference between them, why they are important, and so on. Then we're going to look at the different types, the internal combustion engine or reciprocating engine with a propeller, then the turbojet engine, the turbofan engine, the turboprop engine, and the addition of an afterburner, and how would this affect the fuel consumption. Okay. So propulsion basically is whatever pushes a vehicle forward, whether it's a car, we have a propulsion for the car, or an aircraft, or a ship, or whatever. So it produces thrust. At the end of the day, it produces whatever produces thrust to push a vehicle forward. And the way this is done is that basically we get some medium, some gas, typically air, working fluid, and it's accelerated inside the engine and then dumped from the back, pushing the engine forward by Newton's third law. And this is whatever engine, whatever type of engine we're going to see rely on the same concept. Okay. So whether it's a reciprocating engine, internal combustion engine, just like the one in the car where you have piston going back and forth, rotating a shaft, and the shaft rotates a propeller, or you have a turbojet engine, turbofan, turboprop, they all rely on the same concept. Increase the linear momentum of the gas. That will make a change in the linear momentum, and that will provide thrust by Newton's third law, second law. So the thrusts, fuel consumptions are two words that arise when we talk about the characteristic of the engine. What makes you select one type of the engine, either whether you need a large thrust or it would have a lower fuel consumption. They are the two things that will determine selection of the engine, because they determine basically the performance of the airplane. So let's see, start our first pollen here. Can you raise a hand if you have finished AE 220? Finished, not currently taking, finished AE 220. Good. Okay, more than 2/3, 3/4, and okay, between 70% roughly. Okay, good. So you will know what I'm talking about. We are picking this part from AE 20. So if you definitely one of you can give me the components of a turbojet engine. We're going to start with a turbojet engine. So who would that be? The main components of a turbojet engine. Let's see. Marwan.
Yes, doctor.
Main components of a turbojet engine.
Doctor, I do not remember exactly. I do not remember exactly.
Okay. مصعب. مصعب. Main components of jet engine. مصعب, you are with us?
Yes, doctor.
Okay. You have an answer. When you say jet engine, what comes to mind? Components, what are they? Okay, Abdullah Al-Asmari.
Yes, doctor. I think I
Yes.
have nozzle and diffuser.
Okay.
And, compensator or compressor. I don't remember exactly.
Compressor. Okay.
And yeah, the combustion part.
Combustion.
Burner,
okay.
I think it's called.
So what happened? We have some engine that will take air at low speed and will throw it back at high speed. That's the whole point about thrust. As we mentioned, this is the world of propulsion. In order to do this, we need first three main components, and then we can add more. We need a compressor to keep pressing the air, increasing its density, and thus increasing the mass of air getting inside the combustion chamber. Then we have the fuel combusting the air, increasing in volume, expanding. And as it goes outside, it has to rotate a turbine because I need someone to rotate that compressor. So the turbines will rotate that compressor with them along the same axis or shaft. And then the air will expand, the remaining air will expand through the exhaust, providing the thrust that we have. Okay, so we have the nozzle, as you mentioned here, for the thrust for the exhaust gas to go out. And then we have the intake, or sometimes called the diffuser, where it slows the aircraft. Because remember, this engine is attached to an aircraft that could be flying at a very high speed. So I need to slow that air a little bit before it enters the compressor so that its density increases and it increases even more inside the compressor to get into the combustion. We have the cold section consisting of the diffuser or intake, compressor. Then we have the hot section that starts from the combustion chamber, the turbine, and the nozzle. Okay, so this is what we call a turbojet engine. So the word turbo in any type of engine will mean the three main components: compressor, combustion chamber, turbine. These three. Okay, if you have a nozzle, now it's going to be a turbojet because you have a jet going in there that would give you the thrust. The linear momentum of the air going in is m dot times v. The linear momentum of air going out is m dot times v exhaust. The difference between them is the thrust that's provided on the engine, or that's provided by the engine. Okay, let's see if we can have another.
ما نسمعك يا دكتور.
And you guys.
Yeah, doctor, we can't hear you.
We can hear you now.
What?
We can hear you now,
Okay.
but before it was disconnected.
Oh, is it? Okay. So I was saying if I have a different type of engine, turbofan, for example, what do you need to add to that turbojet to make it a turbofan? So turbofans, how do they differ from turbojets? Sulaiman.
Yes, we add a fan in front of the intake and in the intake.
So what? So a fan. So
Dark fan, so we can have around.
Is that a fan? Is that a fan?
No, propeller.
Propeller. What's the difference between a fan and a propeller?
It allows the air to move inside the engine, but outside the jet, the compressor.
Very good. Inside and outside is the keyword between turbofans and turboprops. In a turbofan, you have, in addition to the turbine, compressor, combustion chamber, the turbine is rotated by the flow of air, then it rotates the compressor, but it also rotates a fan with it. And this fan will increase the speed of air passing through it. Some of this air will go to the compressor, combustion chamber, that's the hot air, but some of it will just go through the blades of the fan and it will accelerate as it does so. Since it accelerates, it will provide additional thrust. Now it's called a fan because the air is still inside the engine. So there is a duct in here in which the air will flow. Okay, so the cold air is ducted and the hot air is ducted. Some of the thrust comes from the hot air and some comes from the cold air. We call the cold air in here, we call it the bypass air because it bypasses the combustion chamber. It's not burned. And depending on the amount of air that's bypassed, we can get different fuel consumption for the engine. Now, the point here is that we are taking some of the energy from the air and we're rotating the fan and giving that energy to the air here to give them thrust. So we're basically getting extra thrust at very low consumption of fuel. We're not using much more fuel. Okay, so turbofans have higher efficiency because we're getting more thrust for low additional fuel. Depending on the amount of cold air to the amount of hot air, we call the engine whether it is a high bypass ratio engine or a low bypass ratio engine. High bypass ratio engine will have more cold air than hot air. Low bypass ratio engine will have more hot air than cold air. So if I call the mass of the cold air per second M cold, and this one is M hot, M cold over M hot, if it is less than 1, it's low bypass ratio engine. If it's more than 1, it's high bypass ratio engine. Okay, high bypass ratio turbofans like this one are almost used in all types of commercial aircraft that you are familiar with. Boeing 737, 4767, Airbuses, all of these use high bypass ratio. We are talking about a bypass ratio of 6 or even more. That means the cold air that goes in here is 6 times the air that's being burned, that burns the fuel and provide the power to the turbine. Okay. So that's why we have these huge fans in there. Most of this air that's sucked by this fan is not going to be used to burn the fuel. Most of it is just going to be accelerating. And we're going to see in a while why is that, why this would have more efficiency than just burning fuel with air and throwing it through the nozzle. Okay, now if this M dot cold is less than M dot hot, then it's going to be called low bypass ratio. That means little air bypasses the engine. Now, what type of applications do you think would use a low bypass ratio turbofan engine? That means I need a small fan, not a large one. Maybe the fan is not going to be from here to here, but maybe from here, just barely to here, a little bit above the compressor. Anyone? What type of application do you think would need a small fan?
Can you repeat the question, Doctor?
The question is, most of the transport aircraft, when you are boarding your flight from here to Jeddah, for example, and you look to your right and see that fan in the engine, it's huge fan, because 5/6 of the air that's being sucked is not going to go through the engine. Okay, but some aircraft would have a much smaller fan, a fan that's barely like a little bit more in diameter than the compressor. So the cold air is going to be much less than the hot air. We call it a low bypass ratio engines. What type of applications do you think would have a low bypass ratio engine? That means a small fan, a small size engine.
I think less fuel consumption maybe, or I think more fuel consumption.
Yeah, but why would someone use an engine with more fuel consumption?
To decrease the noise, maybe?
Not really. In fact, the higher the bypass ratio, the less the noise is.
Maybe to increase speed.
So what type of applications you want to increase speed and you don't care about the fuel consumption?
Maybe
Short,
Yes, military aircraft. Military applications are one application where we really don't care about the efficiency as much as we care about performance when it comes to speed, rate of climb, thrust, and so on. So many military aircraft would have a low bypass ratio engines because you need a lot of thrust, but it would be okay if we're gonna do this at a higher fuel consumption. Okay, and we need a small engine. In military aircraft, I cannot have a huge fan, a huge engine, because it's not going to fit in the aircraft. It's going to make the fuselage of the aircraft very big. The radar cross section is going to be very big, and the aircraft is going to be detectable. Okay. So in the military aircraft, we can see sometimes high bypass ratio engines, but sometimes we see low bypass ratio engines. And in both applications, if we're talking about fighter aircraft, we might have what we call an afterburner as well. Afterburner, basically, we are burning fuel after the turbine. That's why it's called afterburner, burn after the turbine. So as air expands and goes through the turbine, we dump more fuel here, burn it, increase the volume of the air, and expands through the nozzle. Okay, and why would you add fuel here and burn to increase the speed of air, increase the thrust? Why don't we add the fuel, all the fuel here? So let's say I am burning here, whatever, 0.5 kilogram per second, and here 0.5 kilogram per second. Why don't I burn the whole 1 kilogram per second here of fuel and get the thrusts that I need?
Because the material of the engine?
Yes, because the material of the turbine, whatever comes out of the combustion chamber is going to hit the turbine, the first thing. This is the highest temperature on all of the engine. It's not in the combustion chamber, it's at the beginning of the turbine. It's called the turbine inlet temperature. This is the highest temperature in the engine. Now, if material science can provide us with blades that can withstand 4,000 degrees centigrade of temperature, we will burn more fuel here. But right now we're talking about 2,000. So when you need more thrust, I have to burn some fuel here, and then the remainder of the fuel is burned afterwards. The material of the nozzle can withstand that, the material of the turbine cannot. Okay, so with an afterburner, we are going to have like this red and orange streak that's coming out of these tornadoes taking off all the time during the night. So whenever you see that red and orange, that's an afterburner working. And once the pilot climbs to about 1,000 feet, makes the left turn, that's when you will see that flame sometimes goes off because he doesn't need that extra thrust anymore. Okay, so it is a sort of like a thrust on demand. The afterburning provides a thrust on demand, whereas the one from here is a continuous thrust. Okay, so that's it for the turbofan engine. For the turboprop engine, it's the same thing with the exception that the cold air that comes through the blades is not ducted. It doesn't go through the cowling, through the engine if you might still call it an engine. We don't have a cover here as we did in the turbofan engine. So whatever air accelerates through the blades will just go around the engine and go. Most of the thrust comes from the propeller itself. The propeller gets the power from the turbo part of the engine, which is the compressor, combustion chamber, and turbine. So the shaft provides the power to the turbine through a gearbox. Very little thrust is obtained from the nozzle. Sometimes we don't even have a nozzle. It's just an exhaust pipe, just like the exhaust pipe of your car. We're just dumping air outside. We're not getting any thrust out of that. Most of the power is delivered to the propeller, and this accelerates air as well. Okay. So with this turboprop, turbofan, and turbojets comes the question, why do we have all these types of engines? Why we even have in some engines using internal combustion engine, just like the ones in your car, and they rotate propeller. Why is that? Why are all of the types are still working? Why not go for the turbojet, for example?
I think because the different speeds airplanes flying.
Yes, different speed, and how would different speed affect the whole thing?
Different uses for the planes.
Yeah, different uses, that's correct, means a different speed. Some aircraft has to go slow. For example, agriculture aircraft dusting crops with pesticides, they go slow, they fly slow, so they can cover properly. Some aircraft would need high rate of climb, like military aircraft. You need to go faster. Yes, that's different applications. So different applications transfer to us in design in different requirements in terms of speed, altitude, and so on. But the question is, why would that? What effect would that have on the engine? For example, when you board an Airbus 320 from here to Jeddah, the airplane can go slow. We know it goes slow, right? Before takeoff, and it can continue to fly slow all the way to Jeddah, and it can go fast, right? So it can fly for all flight speeds, of course, above the stall speed. But the question is, why would these speed variations make you choose different engines when you design an aircraft? Yes.
Doctor. I think it depends on the engine and the thrust, and eventually you need to use it.
And the thrust what?
Efficiency.
Efficiency is the key word here. Yes. When you say different applications, we mean different speed, different thrusts. Large aircraft, small aircraft, slow aircraft, fast aircraft. So that's the different uses. Almost most engines can fly you for all applications. Okay, but at what efficiency, at what cost, at what price? Okay, so efficiency here is the keyword. Some engines are efficient at high speeds, others are more efficient at low speeds. Okay, so what we are gonna see now is we're gonna develop an equation for the speed and see which engines are good for which type of application. Now, this is important when we are doing preliminary design. Remember, in design, you don't have the shape, the configuration of the aircraft. You have to start from scratch. All you have is requirements. So you are designing an aircraft that has a certain speed, certain altitude. So which engine to choose? So it's important to relate efficiency to these thrust and efficiency, the trade-off that we have. We are going to find that the slow aircraft, slow engines that work at slower speed will have more efficiency. For example, propeller aircraft that are driven by reciprocating engines or turboprops will have high efficiency but low thrust. You don't get much of a thrust of a propeller aircraft, but you have high efficiency at the low speed that you have. So when your application requires high thrust, don't go for that. Then you can go for turbojets, for example, to get the high thrust. but you will have to pay the price that you will be working with less efficiency. And even if you need even more thrusts for certain applications, you will go for rocket engines. Add extra thrust, but again, the efficiency will be poor. Now, when we say rocket engines, we don't mean space rockets as well. We can have like boosters, small rockets attached to C-130 transport aircraft taking off just to increase their speed enough to take off from a short runway. Okay, so we can have large thrust but at poor efficiency, very low efficiency. So let's develop an equation for this efficiency. Now we have an engine, and I don't mean to say that this is a jet engine. No, this is just any engine. It could be an internal combustion engine. It's some propulsive device. It could be an engine just like the engine of your car, and then we are attaching a propeller to it. Okay. In this propulsive system, we have air coming in at velocity v infinity. Well, actually, air is not coming in. The aircraft is moving forward at velocity v infinity. So if we imagine the engine to be static, if we stop, if we take a snapshot, then we can think of not the aircraft moving forward, but the air is moving backward, going through the engine at speed v infinity. Somehow inside, it will accelerate to V-jet. Now, when I say somehow, it could be by compressing combustion chamber going through the turbine nozzle. So that's one way. In that case, it's a turbojet. Or it can be for internal combustion engine by increasing in volume, rotating a shaft and giving a power to the shaft. And then it will be dumped as exhaust. In both cases, if I have air coming out at velocity of V jets coming in at velocity of infinity, then the change in the linear momentum is the amount of force. That's Newton's second law. So the linear momentum at the end, m dot v jets minus the linear momentum at the beginning, m dot vn, is equal to the amount of thrust. That's gonna push air backward or push the aircraft forward. Now, the power that the aircraft will get from that thrust would equal the force multiplied by the velocity. Since the force is t, the velocity is v infinity, the power is t times v infinity. So in this case, this is the power that's beneficial to you. This is the useful power, the one that we got. You move the aircraft with this t at this v. However, this is not the power that's generated by the engine or by the fuel burning in the engine. Well, yes, it generates this, but also don't forget, we have air here that's accelerated. And by accelerating the air, you gave some extra kinetic energy to that air, right? And that extra kinetic energy in the air that's dumped on the back, we didn't use that. We have air behind the aircraft that's moving at a certain speed after it left the aircraft, after it left the engine. And you're not using that energy. You pay that price. If you have someone behind the engine and he feels the motion of the jets of the air, you have paid for that air to move, right? But you're not getting anything out of it. You get a thrust of it only if it's moving inside the engine. But whatever moves here doesn't give you any extra thrust. So the increasing kinetic energy is V jet minus V infinity squared multiplied by m dot over 1/2. We always use m dot, not m, because air is a fluid that's moving inside this engine. So it doesn't have like just a mass, it's a mass per second, mass flow rate per second. Or sorry, mass flow rate is the mass flow per second. So this is the increase of kinetic energy. This is a kind of wasted power or wasted energy that we have not used in here. Okay, so the total energy generated is the useful one plus the not useful one. So if I want to define efficiency, is how much of this energy is used to increase the speed of the aircraft, which is this one, divided by the total. So the efficiency of any engine is the useful power divided by the total power. by the useful power, it's TV infinity. That means m dot v minus v infinity times v infinity. That's the one that we have in the top. And in the denominator, we have the total power generated that we have. We can cancel m dot, we can cancel the parentheses, we can cancel one of the infinity, and this is what we will come up with the efficiency. We'll just arrange the terms, and we're going to have the 2 going up to get the final expression of the efficiency of the propeller. Now, this is one simple equation that I don't need to give to you. It should be on the top of your mind. Efficiency of any propulsive system, of any propulsion, of any engine is 2 over 1 plus V jet over V infinity. Let's see if this equation makes sense. First, is there any question in the derivation of the equation before we start looking at it and see how it's applied to different kinds of engine? Any question in these 2 slides, here and here?
I've got a question.
Yes.
About the equation itself.
Yes.
Does it apply for all engines or just turbojets?
No, it applies for all if you use all power, total generated power, and total useful, one in here. For example, this applies also for turbofans and turboprops, but remember the VG from the hot part will not be the same as from the cold part. So it needs a little bit of adjusting, and we will do this next time. Okay. So it can be applied if I know the average value of VG, for example. Is this clear?
Yes, thank you.
Okay. Any other question? Okay, I have a question for you that was raised in the other section. It says, when we calculate the power equal the force times the velocity, why did we multiply by V infinity, not by Vj? Can anyone answer this question? Very good question, very valid one. Why didn't we multiply the velocity by V jets in order to get the power? We multiplied by V infinity. For the
I think because it's the velocity of the aircraft.
Who is this, Mu'taman?
Yes.
Oh, Mu'taman. Yes, correct, Mu'taman. It is because when you calculate the power, you multiply by the velocity on which the force acts. The force acts on the aircraft, you multiplied by the velocity of the aircraft. Okay, this is actually the velocity of the aircraft. It happens to be the velocity of the entering air because it's the same, but it's definitely not the velocity of the jet air. Okay, so let's look at this expression. We learn from here that you will never have a jet engine of 100% efficiency, because in order to do this, I must have, since I have 2 in here, I must have 2 down there. Since this is 1, so this must be 1. So for this to be 1, V jet has to be the same as V infinity. Air has to exit in the same speed as the entering air, because if it's going any faster, you have lost that energy. So you have to take every single joule of energy in that air coming out. Since we cannot do this practically, because of all the kinds of the losses that are going to have if you add more turbines, then we will never have 100% efficiency. Also, it tells me the faster the air that goes out, the higher this term, the higher the denominator, the less is the efficiency. So that's why when we talked about, let's say, turbofans, we said they have more efficiency, because you see they increase the speed of air, but not much. The air coming out of here is faster definitely than the air entering the fan, but it's not much. Whereas air coming out of the jets is much higher speed, has a much higher speed than the one entering the engine. So the efficiency of the cold part, the hot part, is poor compared to the efficiency of the cold part. so that the net efficiency of the turbofan is high. That's why transport aircraft, where I really don't care much about breaking the sound barrier or going too fast, transport aircraft where I care about efficiency because it's working for an airline that should be profitable at the end, otherwise it will go bankrupt and shut down. So most transport aircraft in airlines would have a high bypass ratio because the efficiency of this part is more than the efficiency of the hot part. Okay. Now we are going slow in this and looking at the ends of it so that we can select the proper type of engine when we have to do design decisions in chapter 6 and 7. Okay, then we have the next part. What if we're not talking turbojets, turbofans? What if we're talking turboprops and internal combustion engine? So in this case, in here, almost all of the power delivered to the air is delivered through the propeller. We don't rely on the exhaust to provide any thrust. Very little thrust, I would say. So the power delivered to the air comes from the shafts. And since we have some mechanical losses in the gearbox, some mechanical losses in the propeller, the power coming from the shaft is not the same as the power delivered to the air. Okay? So it would be wise to talk about the shaft power, the brake horsepower that we have in here. For turboprops, since this power depends on how much air we get inside the compressor, burn and dump through the turbine, this power will be affected by the mass of air. As you go up in altitude, the mass of air will decrease because of the decrease in density. Density of air at sea level is rho naught, which is 1.1 if you are talking kilogram per meter cube, or 0.032 if you are talking British units. But as aircraft goes up, the density will go down. So it's just reasonable to assume that the power generated with the engine will go down from what's generated at sea level. So if you have a turboprop at sea level, generated P naught, as the aircraft climbs in altitude, the power will be P, which is less than P naught. Now, Torenbeck is one engineer that did some calculations regarding the variation of the power with the altitude. And he derived a famous equation, very simple equation, tells me how the power will go down with density. That means with altitude. Okay. So the brake power for internal combustion engines, reciprocating engines, goes down with altitude. However, the specific fuel consumption does not. Can anyone define what's the specific fuel consumption? Assume, since most of you had 220, you still remember that? Specific fuel consumption, what do we mean by SFC?
Specific fuel consumption.
Yes, Fahd. What's that?
Special fuel consumption.
Specific, not special. So what does that mean? Specific. Yeah, what does that mean? Physically, what does it mean? How do you define it?
I think it's depend on how the fuel is consumption.
If it's only that, then we will call it fuel consumption. For example, you say your car consumes that amount, that many liters of fuel per 100 kilometers. That's the fuel consumption.
Okay.
Or an aircraft, if you look in Wikipedia, you will see an aircraft consuming 4 gallons per minute or per hour or whatever. That's fuel consumption. But why the term specific, Nawaf?
Yes, I think it's the fuel consumed for each unit of power.
Yes, that's very good. Specific means the amount of fuel or something, and here we are defining it for the unit of power. So it's the weight of fuel consumed within a certain time to get some power through the same time increment. So it's m dot divided by p in this case. Now, as the aircraft goes up, what happens to m dot? Decreases. What happens to the power? Decreases. So the specific fuel consumption itself really doesn't change that much with altitude. You can assume it's constant with altitude. Okay, so specific fuel consumption is almost the same, but the power itself decreases with altitude. Okay, now how would power change in here? If you recall, or you have seen before, an internal combustion engine that has 4 strokes, as the piston moves up, you are moves down. That's the induction part. We are sucking air. Then we have the compression. It moves up, compresses the air, burns the air. That's when the power is generated, and then the exhaust goes out when the piston rotates and goes up, pushing the exhaust gases through the valves. Now, the power generated in an internal combustion engine or a reciprocating engine, of course, increases with the volume inside. I would say the displacement that we have is a representation of the volume inside. Okay, so the displacement of the pistons with the pressure inside and with the RPM. So how much air you are going to use to fill in here will change with altitude. So that's why pressure will decrease with altitude following the Torenbeck equation. Whereas the specific fuel consumption will remain almost unchanged. So in summary, this is basically what we did today. We looked at the power and specific fuel consumptions. We will select these, we will select engines later on based on both for reciprocating engine or thrust and specific fuel consumption for jet engines. For internal combustion engines, we found that the power does not change with speed, but it speeds with altitude because of the density. And the specific fuel consumption is almost constant, does not change with either speed or altitude. Whereas for jet engines or engines that get most of the thrust from the jet, including turbofan engines, we found the efficiency here decreasing with the jet speed. Okay, so next time, inshallah, we're gonna look into more details on the equations governing the performance of these engines, and we're gonna wrap up our propulsion introduction for the design. What will remain then is the control and flight mechanics introduction. This is basically chapter 4 and 5. And then we're gonna start right away with the design phase, chapter 6, 7, and 8. I think we have a couple of minutes for any questions. No. So those who joined late, make sure you check Blackboard in about 10 minutes or your email. You will get an announcement for homework number 1, which is due next Monday. Then the quiz, which will be due 1 week after that. Yes, Marwan.
Doctor, just want to ask about the...
معلش ما اسمعك.
Sorry, you hear me now?
Yeah, if you can, yeah, okay.
Just wanted to ask about the reciprocating engine.
Yes.
Is it something separate from the other engines, or it can be?
No.
I mean, yeah.
Reciprocating engine is the thing. It is an internal combustion engine, just like the one in your car. Okay. When we talk about the performance of the aircraft, for us it's just like any other engine. It produces some power. Okay. But if we are talking how this power is generated, it's totally different from the turbofan, turbojet, and turboprops. Because there you are simply accelerating air through the fan or the propeller or through the turbine, right? So we are accelerating air. But for the reciprocating engine, in here, maybe I should have talked more about it. What we are doing, we are not accelerating air. What's happening, we are making air expand in a closed confinement, thus pushing on the piston down and rotating the shaft. This is where the power will come from. So it's the underlying concept. We are not accelerating air, we are making it expand at high pressure. Okay, so that's why the word internal, because the combustion is internal, but for the other one, it's external because you are making the air go into the open air to provide you with the thrust. Does this answer your question?
Yeah, Dr. But I'm also asking about, can an aircraft have a turbofan engine and a reciprocating engine? I mean,
well, you can, in concept, you can. That's. I would say turboprop and reciprocating engine maybe, because the flight regime for both is close. But turbofan and reciprocating, I wouldn't, because the flight regime for both is very different. Okay, so reciprocating engine for slower aircraft, turboprops slightly higher, turbofan much higher. So you might have two, but not turbofan and reciprocating engine. I'm saying you can, I'm not saying there is, but you can in concept do that, but you will have to pay the price for the efficiency. Because one of them will be efficient in some part of the flight, the other one will be very low efficiency and vice versa. Okay. Actually, you can mix and choose different types of propulsion. For example, the C-130 I was talking about, it has a turboprop engine, but yet it has a booster, which is a sort of rocket engine, small rocket engine, just to make it take off fast from a short runway. So you can mix and choose different categories. There's nothing that prevents you depending on the application, but you'll have to pay the price in terms of efficiency.
Okay, thank you.
Okay, sure. Any other question? Okay, so I will be seeing you inshallah on Wednesday. I will correct the date for the quiz inshallah. Thank you. Yes.
Did you take the attendance?
I took attendance, yeah. I always rely on the saving the attendees list. So this comes to me automatically.